Welcome everybody to the Cycle 7 Week 3 Thursday MT100-04 Film Room Calibration Standards class that you should be viewing before you come in to mix your film clip either in Studio D Tempe or in Studio D Gilbert. This is all about calibrating a dub stage and a movie theater, which you know, of course, as the B chain. In order to mix correctly at the proper levels, you have to calibrate the rooms so it transfers correctly. This means that if your room is not calibrated correctly, it may not play back. Your film may not play back at the correct volume at various movie theaters around the world. So I always ask the question, who has the volume control at a movie theater? I know it's not me, or I might change some things. But the answer is usually the projectionist. But the projectionist is not supposed to really change the levels. They do have the ability to change the levels, but they shouldn't. They are calibrated to a reference standard. So if enough people complain, then yes, they can go to the master fader section and take off the security cover and trim the levels down. That's usually the complaint. It's too loud. So if they do that, then of course that usually happens during the trailers, and then they have to bring it back up for the feature. So the point being is that if the movie theater is calibrated to a reference standard, the dub stage where you are mixing needs to be calibrated to the same reference standard, so that when you hear something at a specific volume, it is going to translate to any movie theater around the world. And that's what this is all about. These are the SMPTE and THX calibration standards for theatrical audio reproduction. Tomlinson-Holman was monumental in creating the SMPTE standards back in the 1970s. So when he went to work along with George Lucas to create the THX calibration standards, why reinvent the wheel? He used those same standards. And of course, if you're going to be calibrating a room, you need some sort of source material. Each one of these channels is going to be calibrated individually. And what we're primarily talking about right now is 5.1. So our left channel is turned on, calibrated, and then turned off. The center channel is turned on, calibrated, then turned off, etc., etc., etc. So our source material is full bandwidth pink noise. Now this can be a hardware generator or a software generator. Doesn't matter, but you just set full bandwidth pink noise. You send that level out to the left channel at minus 20 dBFS. You send that signal over to the left channel and you set that left channel to exhibit 85 dB SPL. Now you'll notice there's a comma after SPL. That's because there's more information. As you can see, if you're sending that information at minus 20 dBFS, you have 20 dB of headroom. So that means that that left channel exhibiting 85 dB SPL at minus 20 dBFS, if the level goes up from minus 20 dBFS to 0 dBFS, that of course is going to be 85 plus 20 for a maximum volume of 105 dB SPL with no distortion incurred. Now you can always argue that there's going to be distortion in an electronic circuit, and that's true. But if it's going to be 0.01%, you're never going to hear it. So we're talking about audible distortion. Now, you turn that left channel off, and you then calibrate the center channel. You turn the center channel off, you calibrate the right channel. So the center and the right channels are calibrated in the same manner. you still use full bandwidth pink noise, you still set the level at minus 20 dBFS, and the center channel should exhibit 85 dB SPL with a maximum volume of 105. Right channel, same thing. So now we have our LCRs calibrated. Next, we have our surround channels. The surround channels are calibrated a little differently. Our source is full bandwidth pink noise. We still set the level at minus 20 dBFS, but you set the left surround channel to exhibit 85 dB SPL. Once again, we have the comma, so there's more information, and that of course means that if our level goes up 20 dB to 0 dBFS, that's going to give us a maximum volume of 102 dB SPL with no distortion incurred. That, once again, is audible distortion. Some people can't hear distortion until it's 10%. You'll be able to hear it easily at 1%. That left channel then is turned off, and the right channel is calibrated in the same manner. Full bandwidth pink noise, minus 20 dBFS, set it for 82 dB SPL with a maximum volume of 102 dB SPL. The reason we bring the surrounds down in a commercial environment by 3 dB is that there are people sitting at the end of the aisles, and they're closer to the speakers, so you want to bring it down a little. Plus, if you sent 82 dB SPL of noise through the left surround channel and 82 dB SPL of noise through the right surround channel, those then would couple together to give you 85 dB SPL. And that's the level of a screen channel. And you don't want the surrounds louder than a screen channel. And this is strictly for commercial production, movie theaters. If you are doing a mix for home theaters, you do not bring the surround channels down 3 dB. Everything is calibrated at 85 dB. The left, the center, the right, the left surround, the right surround are all calibrated at 85 dB. There's a trend in Hollywood right now that brings the level down for home theater reproduction to 78 dB all the way around. If you're doing a music production, you keep everything at 85 all the way around. If you're doing a home theater production, you set everything at 78. And the reason for that is because we hear differently at different levels. And generally speaking, a home theater is not played as loudly as a commercial theater. So we bring the level down. You probably remember the Fletcher-Munson curves and how our ears hear, how we perceive sound. Now, we have another channel to deal with. That's the LFE channel. The LFE channel is calibrated differently as it goes over to the subwoofer. Our source is frequency-limited pink noise, and this is bandpassed between 25 Hz and 80 Hz. It's a 12 dB per octave slope. It's known as a dual-pole Butterworth design filter for those of you who want a little more information and are taking notes. You send that signal at minus 20 dBFS over to the subwoofer, and that LFE channel shall exhibit 95 dB SPL. Now, we have the same comma here, so if the level goes up from minus 20 to 0, that of course is a 20 dB increase, so that 95 dB goes to a maximum volume of 115 dB SPL with no distortion incurred. The reason we elevate the LFE channel and elevate the output of the subwoofer is because of the nonlinear characteristics of the tympanic membrane on the side of your melon, on the side of the head over here. So we don't hear as well, obviously, in the low frequencies. So we increase the apparent volume to match up our very sensitive mid-range. And now, with all channels operating at 0 dBFS. That means we've got 105, 105, 105 in the front, we've got 102, 102 in the back, and we've got a buck 15 down in the basement. Everything operating at 0 dBFS. The maximum volume in a movie theater is greater than 120 dB SPL. This is a lot of sound pressure level, so please use this for the power of good, not for the power of evil. You can deafen somebody with that much sound pressure level. I understand you've probably heard that the threshold of pain is at about 130 dB SPL, and I think everybody hears a little bit differently. So, 4K at 120 might knock somebody right off their chair. So, this can be a problem with trailers because trailers have the same headroom as the feature. So they're once again, Hollywood is trying to self-govern themselves and bring some of those trailers down in level so that, well, OSHA doesn't come in and say, hey, you can't run 120 dB SPL from a 55 dB SPL noise floor to 120 dB in 15 seconds. So you can bring somebody up to 120 dB SPL slowly, but you don't want to keep it there for any length of time. Obviously, you're going to get hearing damage. Well, where are the measurements taken? You're probably wondering, do I put my calibration mic at 1 inch from the cone of the speaker, or 1 meter from the cone, or maybe out in the parking lot? Where do we put the measurement mic? The measurements are taken at the sync point, and sync point stands for synchronization point. Right? The synchronization point is the point in the movie theater where the audio and the visual elements are in sync. And you would think that the sync would be right up against the screen, but it's not. And the reason for that, if it was in sync at the screen, by the time the sound got out into the theater, you'd be a frame out of sync. That's about halfway into the theater. As the sound continues into the back of the theater, now you're 2 frames out of sync. And people start seeing lip sync errors at 2 frames. So we have to compromise. If you're sitting in the front, right next to the screen, you have to get there earlier to get a better seat. If you're sitting in front, you're actually hearing the sound 1/24 of a second before you see the picture. So, in the middle of the theater, it's in sync, and in the back of the theater, it's out of sync. So at the actual screen, it's 1 frame out of sync. In the middle of the theater, it's in sync, and in the back of the theater, it's 1 frame out of sync. That point in the movie theater is 47 feet from the screen. That's the sweet seats. That's where you want to be sitting. The audio is advanced 1 frame during the layback process to film. Much everything, of course, nowadays is done digitally, but there is a frame difference in our digital audio. And that's so that when you're sitting in those sweet seats, everything is in sync. And that's where you want to be sitting. And that's where the film is mixed. That's where you put that big desk right there on that dub stage. So 47 feet from the screen. Now, let's do a little physics, a little math. First off, the speed of sound is approximately 1,130 feet per second. The speed of light is approximately 186,000 miles per second. Light travels faster than sound. Maybe you missed that class in 3rd grade. We're here to kind of catch you up. Let's build a theater, shall we? Just add water. Okay, now this diagram is not to scale. Although the legroom looks like it's pretty much to scale on some of these theaters around here. But this is a theatrical, this is a stadium seating. As you can see, the seats in the front kind of go up slightly. The seats in the back start to head up, so hopefully you can look over people's hats. And our screen over here, we have a speaker behind that. The time it takes sound to travel 47 feet, 1 frame of film goes by. The reason for this is because film travels at 24 frames per second. So essentially, how far does sound travel in 1/24th of a second? So one frame of film, 1/24th of a second, sound travels 47 feet. Once again, this is not to scale, so don't think that row number 2 is going to be where the sweet seats are. You'll have to go in and measure it. Now, the time it takes sound to travel another 47 feet, 2 frames of film have gone by. So if you were in sync at the screen, it's going to be 1 frame out of sync in the middle of the theater, and then 2 frames out of sync in the back of the theater. And yes, I'm that guy. I go in and measure it. So you're probably going to ask me that. So what you do is you advance the film. You advance the audio 1 frame. So the sound is actually before the picture 1 frame at the screen. The sound is after the picture 1 frame in the back of the theater. There it is, your sync point. So that's where you want to be. The math involved in this is film travels at 24 frames per second. Sound travels at approximately 1,130 feet per second at 70 degrees at sea level. So 1,130 feet per second divided by 24 frames per second gives you 47 feet per frame, or how far does sound travel in 1/24th of a second? 47 feet. And there you have it. Next, we're going to be setting some levels. These are kind of general guidelines for mixing for film from here on out. One thing, I think we can all agree that the most important audio element of a film is going to be dialogue. Because if you can't hear what they're yapping about, you don't know what they're yapping about. You got to be able to follow the dialogue or you won't know the plot. So the dialogue level is known as dial norm. And dial norm stands for dialogue normalization. You have to normalize the dialogue for each specific scene. And this is obviously not something you can go into Pro Tools and click on a clip and go, normalize. No, that's not going to work. It has to be through active dynamic automation for each individual scene. And obviously, a very quiet scene, the dialogue's going to be maybe a little lower, but on a very loud scene, explosions and cannons and dams breaking, it's going to be louder. So you have to normalize it for that particular scene through automation. Now, you're probably wondering, well, how loud should the dialogue be? Well, SMPTE states that the dialogue should be set at a reasonable level. Now, that's rather ambiguous, for an engineer who likes to see meters and voltages and physics. And so what is reasonable? What's reasonable for one person is not necessarily reasonable for another. So they state that the average level of dialogue should be approximately minus 27 dBFS on the dB full range scale. So how does that equate to SPL? You may recall that we're sending minus 20 full bandwidth pink noise to a channel, say the left channel, and that channel should exhibit 85 dB SPL. If we reduce that by 7 dB, 85 minus 7, you're going to get 78 dB SPL. And during our mixing class, when you're actually in here mixing, we're going to use an SPL meter to get our dial norm. So we can get a pretty good accurate representation of where that level is at. In all instances, use common sense. All other levels should be referenced to the dialogue. You notice the different spellings of dialogue. We have dialogue with a U and an E at the end, and then dialogue in this particular instance has no U or E. Either spelling is correct. Setting levels once again. As we said previously, the most important audio element of a film is dialogue. But there's three different ways of using the term dial norm in our world. Di in dialogue normalization, you can mix to the dial norm. When you're mixing to the dial norm, that is you in the room with an SPL meter, and you are actively mixing to the dial norm to get that average level of 78 dB SPL. You can also print the dial norm. And what that means is now that you have your dial norm set, once you do your layback process to film or digital or wherever you're going with this, that is known as printing that level. And you've probably heard that term before. Well, you've probably heard it when you're doing a tape, with analog tape. It's like, instead of let's record it, it's like let's print it. And finally, we have encoding the dial norm. And encoding the dial norm has to do with when you're creating a codec, such as DTS or AC3, and you're taking a file, and when you create an AC3 file, there's going to be metadata inside that codec that's going to allow you to adjust many different things. One of the fields is known as dial norm, and you can say when you are encoding that AC3 codec, you can say in that field, you know what, I'd like to bring this clip up 3 dB, or I'd like to bring it down 3 dB. And you can encode that dial norm so that when the consumer clicks on an AC3 file, maybe that AC3 file is really low in level. Maybe it's, you're doing a Blu-ray disc, and there's interviews with the director, there's interviews with the makeup artist, there's interviews with the sound guy. Maybe the makeup artist's interview is 3 dB, 4 dB low. So with the consumer, when they click on that, they're going to turn it up. Well, when they click on something else, it's going to be too loud. So you can say, I'd like to bring this up 3 dB. That way, when the consumer clicks on that, it's going to match the level of all my other AC3 files. So that's it's kind of an automatic gain control for the consumer when you encode the dial norm. Okay, dynamic moves in film. Some kind of general guidelines when you're mixing for film. First off, volume is considered a dynamic move. Obviously, dynamic range. The general guideline is you don't want any unusual volume changes. And that means you don't want something that's way too loud or way too soft. As they say, you got to get the car door right. People will notice a Mercedes versus a Ford F-150 pickup, that sort of thing. An unusual volume change might be, I happen to have a remote control in my hand right here, and I'm going to put this down. Now in Foley, I'm probably going to get some plastic thing to match that up. But what if I put it down like this? You didn't hear anything. That's an unusual volume change as well. And people will notice that, and that will pull them out of the focus. And you never want to pull the viewer away from the focal point. You want them totally focused and engrossed into that film. So any weird volume change, too loud, there's artistic ways of doing these volume changes that a lot of directors use to create certain emotions and things. Once again, general guideline is you don't want that car door too loud. You don't want that remote too loud, because people are going to think about it and go, why was that car door so loud? Why was that remote so loud? And it pulls them away from the focal point, that being the entire plot of the film. So here's a little trick. When you're mixing for picture, a lot of times we become very myopic. And what that means is that we have like little blinders on, and we're focused on an element of the film, and you you might be compressing that little element and bringing it up and EQing it and bringing it up and bringing it up, and you don't even notice suddenly that it's 9 dB hotter than it should be. So if you close your eyes just for a second, and take away the visual element, whether you're mixing for film, television, whatever visual element, take away that visual element. Now you're mixing a radio show, and you're focused on that piece of audio, and it'll pop out at you. You'll say to yourself, "Oh, that cannon's not loud enough. Oh, that car door is too hot." So close your eyes, take away the visuals, and ask yourself, does this mix sound natural? All right, another dynamic move is going to be panning. And with panning follows the emotional content of the scene. So people will follow panning. When Atmos first came out, it was reported that people were actually, wrenching their necks and looking back when things were flying over the top of them. But the emotional content of the scene means that if you have a very low-key scene, you can't get away with much panning. An example would be maybe a couple of guys sitting on a park bench in a park, where a park bench would be, and they're talking about, what guys talk about. Basketball, donuts, submarines. And for me, that's very emotional. But let's say it's they're just talking about that. And if there's a lot of panning going on in the background, that will pull the viewer away. They'll start following that panning. So a couple of people sitting in a kitchen, very, very kind of low-key conversation, you can't get away with much panning. But in a high-emotion scene, you can get away with plenty of panning. That's the Irish contraction for the word of there, the O apostrophe. Plenty of panning. And any type of high emotion scene. I mean, you've got a battle scene, Saving Private Ryan, classic movie, a lot of battle scenes going on. D-Day, hitting the beach, man, that was an intense movie. You got stuff flying everywhere. You can get away with a lot of panning. And your clip that you're doing today is a bit of a hybrid. It's kind of low emotion. There's a few things going on that you can pan around, and you should have fun with it. And automate some panning so that some fireworks fly across the screen. One last thing about panning. You don't want to pan dialogue into the surrounds unless the scene has been set up for it. It's really weird to hear dialogue behind you, coming from behind you. It creates something known as the exit sign effect. If the scene is set up for it, like, you've got a shot where you can see the students in the classroom, you can see the screen, it's a classroom, and then they cut it to just the screen, well, it's been set up. You already know that there's students behind you on that next shot, and so if students start talking, it doesn't bother you. If you got group walla, you're at a cocktail party, you're in a New York street scene, people are going to be talking behind you. But if it's not set up that way, it creates the exit sign effect. And the exit sign effect is the natural tendency for a human to turn around when they hear voices behind them. It's really strange. So the exit sign effect is a term that was coined by Tomlinson Holman, the modern father of surround sound. And the reason they call it the exit sign effect is because in the old theaters back in the day, before they had the stadium seats, you would always go into the back of the theater and walk down towards the screen and get your seat. If you ever turned around in those old theaters, what would you see? The exit sign. And that's why they call it the exit sign effect. That concludes our presentation, and I'm looking forward to seeing your film clip, and we'll be giving you some pointers and some techniques on how to get your dialogue, get a greater amount of intelligibility with your dialogue, how to get the music so it sounds a little fuller, and how to get your sound effects onto the screen, and then also how to do some automation. So looking forward to seeing you on Thursday, week 3.